Hi everyone, welcome to video lecture series on Basic Electrical and Electronics Engineering course, Session 3. I am Dr. D. Srilata, Professor of EEE Department, Vasireddy Venkatadri Institute of Technology, Nambur. Now in this session, I'd like to talk about various kinds of network elements, their classifications, properties, as well as Kirchhoff's laws. So these are the contents which we are going to discuss in this session now. So first one, let us step into the topic, that is classifications of active elements. Already we have seen in the types of elements, elements are classified into two types, active elements and passive elements. The active elements are the elements which will supply energy to the loads. So these active elements are usually classified into two types. One is dependent sources and independent sources. Dependent sources and independent sources. What are the dependent sources? These are the sources which are dependent on some other quantity in the same network, either voltage or current. Dependent sources are the sources which depends on, that is whose magnitude is depends on any other quantity like voltage or current in the same network. And usually these dependent sources are represented with the symbol diamond. So here this is the diamond symbol representation for all the dependent sources. Next, for independent sources, these are the sources which are independent on any other quantity, irrespective of any other quantity in the network. The magnitude of either voltage or current are going to be fixed. For example, if it is an independent voltage source whose magnitude is 10 volts, that means the 10 volts magnitude constantly supplied by the source irrespective of any other voltage in the network or any other current in the network. So such kind of sources are said to be independent sources. So all the independent sources are denoted with the symbol circle. This is the symbolic representation of independent sources. So all the dependent sources are shown by diamond and all the independent sources are shown by circle. Next, coming to the classifications of dependent sources. Here all the dependent sources are classified into two types, basically dependent voltage source, dependent current source. And these dependent voltage sources, basically these are the voltage sources. These are the voltage sources, whereas this voltage source is a dependent voltage source, is denoted by the symbol diamond, and the magnitude of this voltage is V. But here it is dependent on some other parameter. Since it is a dependent voltage source, so the magnitude is voltage here, and if it is a dependent current source, we need to represent a source with an arrow mark. So it shows a dependent current source. Simply a dependent voltage source is represented with a diamond symbol with plus or minus, and a dependent current source is represented with an arrow mark which shows the direction of current in the branch or in the source. Next, dependent voltage sources are classified into two types. One is voltage controlled voltage source, current controlled voltage source. Being it as a voltage source, here you can observe the difference. It is a voltage source which is controlled by some other voltage in the network. It is controlled by some other voltage in the network. For example, if I take a voltage source whose value is dependent on some other voltage in the network. Let us say here V is the magnitude of voltage supplied by the source, but it is not constant value. It depends on some other voltage Vx in the network. For example, here we have any other branch. Let the branch voltage is Vx, whereas the magnitude of this voltage V is dependent on this Vx value. So it can be represented as V is equal to K times of Vx. So it doesn't mean it is a voltage dependent voltage source. Next, current controlled voltage source. That is, here it is a current source, it is also a voltage source, but whose value depends on some other current in the network. That is, V is equal to some K times of Ix. Here you can see this is a voltage source whose magnitude is not fixed. It depends on some other value of current in the network. For example, we have any other branch which is connected to that source. If let us say this is Ix through that branch, then the value of voltage of this source depends on current flowing through this branch. That is, this voltage depends on some other current which is controlled by some other current. So that's why it is called current controlled voltage source. Similarly, we have dependent current source also. This is dependent current source. Since the dependent current source is represented symbolically with a diamond shape, whereas internal to that diamond shape we represent the direction of current. Here these dependent current sources are again classified into two types. One is voltage controlled current source and current controlled current source. So VCCS, voltage controlled current source, current controlled current source. So in these two cases, it is a current source, that is, whose magnitude of current depends on voltage, that is, which is controlled by voltage. So that's why we can write this I is equal to K times of Vx, and in this current source, current controlled current source, the magnitude of current supplied by this current source depends on the magnitude of current. So that's about the classifications of dependent sources. Dependent voltage source and dependent current source. So these are the classifications of dependent sources. Next, coming to the classifications of independent sources. Independent sources are classified into two types. One is ideal voltage source, practical source. Independent sources are classified into two types, ideal source and practical source. Again, these ideal sources are classified into two types, ideal voltage source, ideal current source. And practical sources are again classified into two types, practical voltage source, practical current source. We have two different types of independent sources, ideal as well as practical. Again, ideal sources are of two types, ideal voltage, ideal current. And practical sources are of two types, practical voltage and practical current. And let us see what are these voltage sources. Ideal voltage source is a voltage source whose magnitude is going to be fixed. And the internal resistance of this ideal voltage source is, here we need to represent a short circuit. Short circuit means internal resistance of this ideal voltage source is 0. And coming to the practical voltage source, the internal resistance is connected in series, is represented in series with the voltage source, ideal voltage source. That is the major difference between ideal voltage source and practical voltage source. In ideal voltage source, only the magnitude of voltage is represented without any resistance. That is, internal resistance of ideal voltage source is 0. But in practical voltage source, a resistance, internal resistance of the source is represented in series with the voltage source, ideal voltage source. Okay, here that is ideal voltage source and practical voltage source. Whereas in ideal voltage source, since the resistance is 0, whatever the source voltage, it will be appeared across the terminals. That is, Vt is equal to Vs. There is no drop. But in practical voltage source, voltage across the terminals Vt or VAB is equal to Vs minus I into Rs if there is any load connected across it. If let I is the current, then Vt is equal to Vs minus I into Rs. This is the expression for voltage at the terminals. This is the expression for voltage at the terminals. Then if you come across the characteristics of this ideal and practical voltage sources, see, so in this characteristics, here in case of this ideal voltage source, it supplies a constant voltage at the terminals. But in case of practical voltage source, if this is Vs, then Vt will be like this. That is, as we know, in case of practical voltage source, Vt is equal to Vs minus I into Rs. Whatever this drop has to be subtracted from the source voltage. So it is Vs and this is I. If I goes on increases, because of this drop I into Rs, the drop will be subtracted from Vs, then we will get the terminal voltage. So this deviation will be I into Rs. So like this you will get the volt ampere characteristics of practical voltage source and ideal voltage source. Next, coming to current sources. We have two different kinds of independent current sources. One is ideal current source and the other one is practical current source. Now, an ideal current source whose internal resistance is infinite, because there is no internal resistance, it is infinite, and whatever the current source value, it is flowing at the terminals also. It is always supplying a constant magnitude of current at the terminals, since its internal resistance Rs is equal to infinite. But in case of practical current source, we need to represent the source resistance or internal resistance of the source in parallel with the ideal current source. Here we have an ideal current source, and in parallel with that ideal current source, we need to represent some internal resistance. So this combination of ideal current source with its internal resistance in parallel is said to be a practical current source. Okay, so if Is is the current, then this I is the current flowing through the internal resistance, then It be the current flowing through the terminals, at these terminals. Now, for this practical current source, we can see if any load is connected here, then Is will be equal to I plus It. So this is the expression for current, terminal current for a practical current source. Is is equal to I plus It. This is the total current supplied by the source will be equal to current flowing through the internal resistance and the terminal current. Now, here we can compare the practical sources and practical voltage source and practical current source. As we have seen in the previous slide, practical voltage source is an ideal voltage source in series with some internal resistance, and a practical current source is nothing but an ideal current source in parallel with some internal resistance. In practical voltage source, resistance is in series, and in practical current source, resistance is in parallel. That is the difference we need to observe in both the cases. Now let us discuss about the source transformation technique. What is source transformation technique means? We can transform a practical voltage source into a practical current source, and vice versa. A practical current source can be replaced with a practical voltage source. So that we can name it as source transformation technique. Means the response of the two networks should be same. Then only we can transform a practical voltage source into a practical current source. So here we can see the mathematics involved in this source transformation technique. Let us see the analysis. Here if you see the voltage source in series with the internal resistance, and here we have connected some load resistance. Then Vs is the voltage source and Is is the source current. The same will be flowing through the load series internal resistance, and then IL will be the load current. Then from this we can write Is is equal to IL. Here this Is is equal to IL. Then what is VL? VL is the voltage across this load resistance. Then VL is equal to whatever the current flowing through the load, IL times of RL. So we got this VL equal to IL into RL. Then VL is equal to Vs minus IL into Rs. What is Vs? This is Vs. And we can remove this drop, whatever the source voltage, from which we need to remove the drop. What is this drop? IL into Rs. So Vs minus IL into Rs, which gives this load voltage VL. Next, coming to a practical voltage source here. This is a current source, ideal current source. In parallel with, we have represented a source resistance, and Is is the supplied current, and I is the current flowing through the internal resistance, and IL is the load current. Now from this circuit, we can write Is is equal to I plus IL. Right? We can see the source current Is is equal to I plus IL. Then what is VL? VL is equal to the current flowing through the load resistance, IL times of RL. So IL times of RL, it doesn't mean I into Rs, because these two branches are connected in parallel. Then voltage across these two branches are same. So I into Rs is equal to IL into RL. So after getting this expression, we can write the expression for voltage VL as I into Rs. Then instead of I can substitute. I is equal to Is minus IL into Rs. Okay. Then I hope you understand what are these equations. Then VL is equal to Is minus Rs. You just multiply this Rs into these two terms. Is into Rs minus IL into Rs. Okay. Now we got this expression. VL is equal to Is into Rs minus IL into Rs. Once if you observe these two expressions, expression 1 and expression 2, you can compare these two. These two expressions are same. Expressions in the sense the load voltages or output responses will be same whenever Vs is equal to Is into Rs. This is the conclusion. So these two circuits are equivalent whenever Vs is equal to Is into Rs. Okay. So for example, if we have this current source, now I would like to transform this current source into voltage source, then that equivalent circuit can be represented like this. But we don't know what is the value of this Vs. Vs can be determined by knowing this Is value and Rs value. Simply I'll get Is into Rs, which gives this Vs value, and whatever the internal resistance, that internal resistance will be kept in series with the voltage source. So in this way, I can transform a practical current source into practical voltage source and vice versa. The same way, if I have a voltage source, if I have a practical voltage source, then I can transform this practical voltage source into practical current source just by knowing this Is value. Whereas Is is equal to Vs by Rs. What is this Vs? Vs is this value. Now from which I can calculate Is. Then whatever this internal resistance in series with the ideal voltage source, that can be connected in parallel with this current source, so that I can transform a practical voltage source into practical current source. So I hope you understand. That's all about the source transformation technique. So now in this, just I am going to transform one practical voltage source into a practical current source and the practical current source into a practical voltage source. This is happening whenever the two responses are equal, so that we can say a practical voltage source is an equivalent circuit to a practical current source. Next, let us go for Kirchhoff's voltage law. and Kirchhoff's current law. Before going to this voltage law and current law, we know about these Kirchhoff's laws. What are these Kirchhoff's laws? Kirchhoff's is the scientist name. A German physicist, Gustav Robert Kirchhoff, who introduced the laws of circuit analysis. In order to analyze any electrical circuit, he proposed two different laws. These laws are known as Kirchhoff's laws. And namely, those laws are Kirchhoff's voltage law and Kirchhoff's current law. Now let us see what are the statements and how to apply these laws to an electric circuit. So first let us see what is Kirchhoff's voltage law. Kirchhoff's voltage law states that, this is the statement. So we can read, Kirchhoff's voltage law states that algebraic sum of voltages within a loop or a mesh is equal to 0. Algebraic sum of all the voltages within a loop or mesh is equal to 0. So, for example, for the understanding purpose of this Kirchhoff's voltage law, I have taken a simple circuit. There is a basic circuit which consists of one voltage source, two different resistances. Let us say R1, R2. These two are connected like this, forming a simple loop. So first thing, what we have to do while applying this Kirchhoff's voltage law, or in short form we can name this as KVL. So here, depending upon the direction of current, we can say either that is voltage rise or voltage drop. Here first of all, we need to assume the direction of current through a loop. Here once you can observe, this is a closed path. I am assuming that current is flowing in clockwise direction. So that this is the direction of current through all the resistors. And the direction of current through the source is also like this. Now, here Vs is voltage rise and V1, V2 are voltage drop. What is Vs? Vs is the source voltage. V1 and V2 are, this is V1. V1 is the voltage across resistor 1. V2 is the voltage across resistor 2. These are the two voltages. Now, we have three voltages in the network. One is Vs and the other one is V1 and V2. Once if you observe the direction, before going to know the voltage rises and voltage drop, we need to assume the direction of current either in clockwise or anti-clockwise. Depending upon the direction of flow of current through the resistors, we need to make the sign convention. Here the current is flowing in this direction. So plus 2 minus. And here also the current is flowing in this direction, plus 2 minus. But for the source, the sign convention is given. We shouldn't make the sign convention. That means the voltage source which is having anode and cathode. Anode is positive plate and cathode is negative plate. We shouldn't change the sign convention. So after knowing the sign convention, if current is flowing from positive to negative, then it is called voltage drop. If current is flowing from negative to positive, then it is said to be voltage rise. Okay. If current is flowing from positive to negative, it is called voltage drop. If current is flowing from negative to positive, it is said to be voltage rise. That is higher potential to lower potential. And here is from lower potential to higher potential. Its voltage rises. Then we can see here both V1 and V2 are voltage drops because in V1 and V2 current is flowing from positive to negative, positive to negative. But in case of voltage rise, current is flowing from negative to positive. This is from negative to positive. So Vs is voltage rise, V1, V2 are voltage drops. Okay. Now, all the voltage sources rises are taken as positive. If all the rises are taken as positive or negative, we can make any sign convention. And all the voltage drops are taken as negative. According to that rule, voltage source value, that is Vs, is voltage rise, it is taken as positive. And voltage drops are taken as negative. So it becomes plus Vs minus V1 and minus V2. So hence it is equal to 0. Algebraic sum of all the voltages within a loop or a mesh is equal to 0. Now from this we can write Vs is equal to V1 plus V2. That is, these are all rises and these are all drops. So sum of voltage rises is equal to sum of voltage drops. That's about Kirchhoff's voltage law. Next, from the Kirchhoff's voltage law expression, that is, we have Vs is equal to V1 plus V2. That is, voltage rise is equal to voltage drops. Positive sign is taken for voltage rise and negative sign is voltage taken for voltage drop. So mathematically that algebraic expression can be written as summation k equal to 1 to n plus or minus Vk is equal to 0. What is Vk here? K equal to 1 to n are the number of branches and Vk is the voltage of kth element. Voltage of kth element in a branch. Like that, we can sum up all these voltages V1 plus V2 plus V3 plus Vk, and all these voltages are plus V for voltage rise and minus V for voltage drop. Then we will get the algebraic sum of all the voltages within that loop is equal to 0, where K is equal to 1 to n, where that loop consists of n number of branches. Then n number of branch voltages are sum is equal to sum of all the n number of branch voltages are equals to 0. That gives the Kirchhoff's voltage law. Next, coming to Kirchhoff's current law. Let us see, what is Kirchhoff's current law? Kirchhoff's current law states that algebraic sum of all the currents flowing through branches connected to at any node is equal to 0. Kirchhoff's current law states that algebraic sum of all the currents flowing through various branches connected to a node is equal to 0. Here you can see this is a node. This is a node in a network to which all 5 branches are connected. That is I1, I2, I3, I4, I5. These are the 5 branches, and I1, I2, I3, I4, I5 are the currents flowing through their respective branches. And here, while applying Kirchhoff's current law at any particular node, we need to assume that all the, you can see here, all the red arrow marked currents are flowing away from the node, and I1, I3, I4 are the currents flowing towards the node. Some of the currents are coming towards the node and some of the currents are flowing away from the node. So here, for the understanding purpose, we need to assume the currents flowing towards the node are taken as positive and the currents flowing away from the node are taken as negative. So then we can write the algebraic expression. What are the currents flowing towards the node? I1, I3, I4. So here I1, here I1, I3, I4. I1, I3, I4 are the currents flowing towards the node. So they are taken as positive. And the remaining currents I2 and I5, this red mark currents I2 and I5 are flowing away from the node. These are taken as negative. So that's why I2 minus I5, minus I2 minus I5. This is the algebraic sum. That means we need to make the algebraic sum, means we need to make the sign convention. We need to consider the polarity of the current, the direction of current. So here we can see the currents coming towards the node is equal to currents flowing away from the node. These are the currents coming towards the node and these are the currents flowing away from the node. So from this we can say sum of the currents entering at the node is equal to sum of the currents leaving the node. And these two laws, whatever we have discussed in this session, Kirchhoff's voltage law and Kirchhoff's current law, these laws are useful to analyze the response through any network, and also which are useful for finding the unknown loop currents and unknown node voltages, which is extended to nodal analysis and mesh analysis. And these Kirchhoff's laws are basic laws for analyzing any complex network simply by applying KVL and KCL in a loop or at a node. That's all for today's session. I hope you understand, and let us continue other session.